morning. I never attend a conference. This is kind of opening. It's great. Thank you. My name is Leung. I'm at Imperial College. And it's great. It's my great honor to be here. It's my first time attending this conference. It's great to see colleagues from different parts of the world coming. And I'm going to talk about something which I have worked on for some time, optimization, machine learning, particularly. In this speech, I would talk about federated learning. And this is a computer conference, so I would like to emphasize a bit on the edge computing, which is computation carried out over the network edge. And because of the network edge, usually include, for example, wireless communication, mobile communication with limited resources, communications or computation or otherwise. So it's actually posed very challenging problems for us. So I will talk a little bit about that throughout my talk. Okay, here we go. Here we go. This is an abstract way to represent resources. We all know that. Computation resources, computing resources, always a finite capacity, finite amount available. And we have many users competing for the resources. And how we can allocate them. And some people would grab some of the resources, some happy, some are not happy, and because they didn't get enough of what they want. So often we would look at some sort of formulation to optimize the allocation of limited resources to meet different demands. Now, this is a very abstract way to present this. But imagine all these resources can be computational resources, communication resources, software resources, sensors. It's very generic. We still need to look at this kind of allocation issue. So often when we deal with this kind of allocation, we formulate it with mathematical formulation. Formulated as optimization problem, and then we solve the optimization problem as a way to help us allocate resources. So at this part of the talk, I would like to describe how we can use machine learning method to solve optimization problem, okay? Particularly to solve optimization problem related to resource allocation. Okay, it's a piece of work collaborating with my colleague listed here. Okay, if you allow me, I would dive into some mathematics, but don't be scared with it. I will try to interpret the physical meaning of the mathematics that's related to the problem we are dealing with day in, day out, whether you are working on computer systems or your communications networks. So here's the problem we try to solve. Okay, we have some control variables, x, which is you can think of this how the resources will be allocated to different demands. And so according to some allocation, you have some value of doing the allocation. We call this function f. So essentially, we want to either maximize the utility, the maximization, or some sort of a penalty in your allocation. And as a result, you want to find the optimal way to do things. Either maximization or minimization, doesn't really matter. You just add one sign into it, that would be maximization, would become minimization problem. So you can see here, you have the constraint. The set of constraints represent we have limited resources. We cannot allocate more than what we have. Essentially, this is the constraints. So this kind of a problem is very generally applicable to many settings. So this well-known optimization problem. But the problem is this. I have not told you about the mathematical property of this objective function f. I haven't told you about the constraint functions h. And because of that, then some existing technique has been proposed is using Lagrangian multiplier to kind of combine the objective functions and the constraint together to have one single equations, J, and then you can solve the optimization, another related optimization. Given the objective function, the optimization problem is given at the top. So we call this primal problem P1, and then the corresponding problem is a dual problem. In general, we know how to solve equations with only one equation. We don't know how to deal with a set of equations which can be included in the constraints. You can have a set of constraints, equations. So we know how to solve this dual problem, but solving the dual problem doesn't mean that you solve the original problem you want to solve. Okay, that's the challenge. So it turns out there's some theory called duality theory, which enable us to solve the dual problem. Solving the dual problem would be the solution for your primal problem that you want to solve. So we have the original problem, and this is the dual problem. But solving the dual problem, we have trouble because this particular constraint is because of the way we introduce, has to be bigger than or larger than 0. So you know that when we deal with machine learning, and we need to have some degree of continuity in your mathematical property, and this constraint of Lagrange multiplier bigger than or equal to 0 is kind of a nonlinear at the point exactly 0. Then that's the challenge. So we managed to convert this dual problem into another problem, P3, and then we can solve P3 by machine learning. And then by some mathematical property called dual problem, solving P3 would be the solution for your original problem you want to solve. Next one. How can we solve it? We use machine learning techniques. So particularly, we want to use long short-term memory coupled LSTM to solve the problem. So essentially, you can think of this is to solve the part of the problem and then iterate it to the next stage. And then we are able to find the solution of your original primal problem. Next, please. We do have a mathematical property, a mathematical issue we have to deal with is the nonlinearity of the lambda, the Lagrange multiplier. But we have a way to handle it. Next slide. I just want to show you the value of doing machine learning to solve optimization problem. I would like to draw the attention to this particular plot. Horizontal axis is the amount of CPU time, the computer time we spend in solving a particular problem. The vertical axis is the mean relative accuracy. In this particular problem, we managed to find the true optimal of your objective function, your true optimal solution. And then we compare the solution obtained by the different methods with this true optimal. So that means you can do better than, in this case, you can do better than the true optimal in terms of maximization problem. So the maximum is 1. And you have different method, okay? So the way our method is the blue curve. So that means I give you one second of CPU time, and you run different method using one second of CPU time. This would be the relative results, relative to optimal. So you can see our proposed method, we give you closer to the optimum than any other existing method. But that's also important. The other important way to look at this curve is, let's say we are engineers. I don't need true optimal. You give me 98 percentile solution. I would be happy already. So let's say I'm drawing a line, 0.98, okay, horizontally. Then you can see different methods may require different amount of CPU time to solve, and our method is actually require much shorter CPU time to solve. So that is the value. So essentially, using this method, we are no longer just interested in finding the true optimal. We are interested in finding good solutions. And maybe 97 percentile best solution is what you want. That's okay. We can give you the solution according to what you would like to have, okay? So this is the beauty of this new method. Move on. Now, with the resource allocation method we just introduced, we know additional way to solve resource allocation problem. Okay, now I would like to move on to another aspect, which is machine learning. Particularly, it's a form of federated learning. Next slide. So the idea is this. We all know that we have sensors. We have different ways to collect data. Maybe there's compact camera mounting at the traffic light, looking down to the traffic conditions, and then you try to learn the conditions. But you have different sources of data. And in the network conditions, so you may have different network, parts of the network belong to different owners. BT and some other companies may have their own network, and they have a lot of data related to their network, and they don't want to share. But yet, they are willing to learn together. Okay? That is the concept of federated learning given here. So essentially, you have a lot of data collected at different places, but we want to do some local processing, process the local data. But yet, the partially learned model need to be aggregated together to have a big picture of the overall situation. So that is the idea of federated learning. And also, federated learning is distributed in the sense that we have local processing the local sensing data in a distributed way. Although we also need to have a central controller. That is the original form. But of course, there are some other techniques we can try to decentralize it. But I focus on the centralized version of it. But for the the edge computing, we have very limited limitation on the availability of resources. Maybe you don't have enough bandwidth. Maybe you don't have the computational power. Maybe the requirement is, I need to get it done. I need to get the learning done within a certain amount of time for your applications. So we have limitation. We have a constraint. And it turns out this problem is, was open for quite some time, even though federated learning was established probably 2016, 17, and at that time when we worked on the problem, there are a lot of open problems related to solving federated learning when we have constraints. Next one. So what we do is actually, we try to tackle the problem. We try to formulate the problem also as optimization problem, okay? And it turns out the optimization problem is difficult to solve. Even though what we just described using machine learning, we won't be able to solve this problem because the function is so complicated. We can't even write down the form of the function, objective function. The function is related to the quality of your learning. So instead, we do an approximation on the right-hand side, and then due to the approximation, we can solve the problem approximately, but yet there's still a lot of parameters which we don't know, but we can measure in the real environment. Next. So once we established this algorithm, we implement it, and in this case, we look at the recognition of handwriting. The MIS data set essentially is you have digits of 0 up to 9, but written by many different people, different style, and you try to recognize the digit. And we can come up with some, we can adjust different parameters to see whether our method can give you the optimal solution. The vertical axis is called a loss function. Essentially, it's the measure, a measure of how effective, how close you are representing the reality. And so obviously, the loss function would be the lower the better in terms of the learning capability. So you can see our solutions represented by the symbols are essentially always give you the optimal solution because we start off by optimizing the problem to start with. So all these results indicate our method, this new method is good. So that means we can do federated learning over the network edge with constraints included. Let's move on to the next slide. Now, we all know these days, I'm sure you heard so much about, I saw there's some papers talking about large language model. We are talking about models of billions of parameters. It's not easy to send that much model parameter over the wireless link at the network edge. So the next step of what we do is actually to look at how we can improve our federated learning by a concept of model pruning. So you can think of it, the left-hand side here, here's the model. This is a neural network model with so many layers, so many parameters. You're talking about billions of parameters, all right? But many of the parameters, you don't need to communicate. You can throw them away. It would not affect the effectiveness of your model that much. So as a result, after you prune all those unnecessary parameters, you have much simpler model to learn, to communicate in the process of federated learning. So that is the pruned model on the right-hand side. And that is sufficient because many parameters is not necessary to be considered carefully. So this is the concept of model pruning for federated learning. Can I go to the next? Okay, then you can ask, okay, if I have a pruned model, how good is it relative to the optimal, to the best? So here is the time we run our different learning methods, and the vertical axis is the accuracy. So the accuracy is actually being able to identify. In this case, it's also digit recognition. The higher, the better. So you can see our pruned model give us the best performance relative to other existing method. That means the lesson is we can throw away a lot of parameters, model parameters. It will not affect your underlying performance that much if we do it carefully. Okay, so that's the concept of the merits of model pruning. One more slide, next slide. Now I would like to introduce one more concept of improving our learning, the concept of model splitting. Okay, imagine I have a very large model, neural network model. If I communicate all the model parameters, you are talking about a huge amount of data to communicate your model, especially when the communication is between a handheld device and the network, okay? So how about this? How about we divide up the model into two parts? One part is stored in the device, let's say the base station, or somewhere in the network. The other smaller part of the model is actually sitting on your mobile device. Your mobile device has limited resources, computational power, communication bandwidth, but the part of the model that's sitting in the base station, presumably you can have much more resources to handle. So this is the concept of split federated learning. So it turns out, indeed, we can actually can generate very good results. Essentially is trading communication and computation. So depending on how you split it, so in some sense, you can have a lot of very little computation at your mobile device because you ship most of the model at the base station, for example. Then the mobile device have little computation, okay? But yet you need to have a lot of you need to ship a lot of model parameter back to the central controller. And then you have a trade-off between the curve, computation and communication. So you can see your total cost is the sum of these two curves. So you can see the sum of these two curves has a U shape, has a V shape. And then the lower energy, the consumption is at the bottom of the U shape. And that is what you would like to operate, okay? So that means indeed, split learning is very helpful. All right, I close. So I have mentioned about how we can use machine learning to do resource allocation and open up new ways to do resource allocation, not necessarily aiming at solving the optimal, but 99 percentile solution, 97 percentile solution. And also introduce the concept of federated learning under resource constraints. And also to handle the constraints we have, resource constraints we have concept of model pruning to remove parameters which is not necessary without affecting your performance. We also have model splitting, essentially is to split the model according to where you think the computation and communication trade-off would give you the best performance. And the problem is not solved. There are a lot of research issues. My students, PhD students, are working on their thesis. So there are wonderful open issues need to be tackled. So I end here.
Thank you very much.
Thank you. Thank you very much, Professor.
Okay.
Yes, we have time for some Q&As.
Yeah.
Any questions coming from the crowd? We really want to open things up and get the dialogue going. So thank you very much for kicking things off. Your name, sir? Your name is David.
David Corliss, Graphic Analytics. You talked about pruning and by reducing the number of features. Reminded me a little bit of some of the things that you do with decision trees, how you use that for pruning, but I hadn't seen it in this before. It's very interesting. How do you tell how much pruning is enough versus too much? You say, oh, it doesn't really affect, I understand that. What criteria do you use when you're implementing pruning to find out the features that really aren't contributing to the neural net? Thank you.
Thank you. It's actually a very, very good question. The method we propose doesn't deal with the particular feature per se. Okay, we just look at measure the parameters that we want to prune, and also measure comparing with the final, let's say, model accuracy as a parameter. So in some sense, we don't particularly think of the application we have in mind. But what you just said could be a possible way to look at the features. But that is not what we did. But it's a possible direction for further work in that area. Thank you.
Thanks for your question. Any other questions? Hands up, please. I'll come run to you. Hi. There you go. And your name, please?
My name is Samrat. So the main question I had was, what are the advantages of using federated learning for this system as compared to using, let's say, a standard centralized system itself, using LSTMs especially?
Could you repeat the last part of your question?
So when using federated learning, as you said before, I think I've used it a few times, but the idea is to effectively distribute your resources across multiple systems and then use an aggregation function in order to get a centralized model of sorts that you can cycle over and over again. So my question here was, is there any particular computational reason or advantage gained by using federated learning, or any sort of performance advantage gained by using federated learning as compared to doing it centrally, rather than just the advantages of being able to do it for edge devices alone?
Well, I think if I understand your question properly, essentially is where can we apply federated learning, given that it has a central controller? Is there any other alternative we can do machine learning other than federated learning? federated learning is one particular form of learning, okay? But I give credit to the federated learning. Particularly, I heard there are some defense colleagues within the audience. The good part of federated learning is the data, the local data, will be processed locally. We don't share the raw data. And that, especially for defense, even for civilian applications, we ask BT, their network, would you like to share their network data with another competitor? BT would say, no, sir. But they're willing to learn from their local data and share the model parameters with others, okay? I think that is a very important, data privacy is a very important feature of federated learning. The second part of the question you mentioned is whether we can, how we can apply it when we have a centralized controller in aggregating the models from different clients. And there are different ways to handle that. They have decentralized the federated learning, first of all. Secondly, federated learning is only one form of learning. You have many other forms. You have reinforcement learning. You have other form of learning which doesn't really constrain yourself to be centralized. You can actually have multiple agents learning which is actually distributed. But federated learning has its own merits for some applications.
Thank you.
Thank you. Thank you. Maybe time for one more quick question, possibly? Yes, right at the back, of course.
Yeah.
Here you go. Thank you.
Thank you for the interesting talk. Yeah, my name is Andreas, and a follow-up basically to a previous question that was asked regarding the criteria of the features that you're pruning.
Yeah.
Have you considered there that dealing with this can also be for explainability purposes? For example, add a feature where you can justify which features are more useful or will make the model more efficient, and how to reason about them, and so give the client the opportunity to play with this, modify all these features that can be pruned, so it can make also the process more transparent. Yeah, that's it basically. Thank you.
Oh, thanks for your question. As I mentioned earlier, our method doesn't deal with features because features depends on the specific applications. When I have vision problem I have to deal with, then for different type of applications, I have different features. We are not dealing with application-specific features in our pruning process. We just look at the ultimate performance measure. For example, the accuracy of pattern recognition. That's the ultimate user-specific performance objective relative to the changes of parameters or deleting some parameters, how those deleted parameters would affect the ultimate performance. So we are dealing with much more, much more generic, much more non-application specific pruning. But if you want to deal with the features, of course, that would be another line of research that we need to work on.
Well, thank you very much. That's all we got time for the questions. Can I have applause one more time for Professor Leung?